Apologies, first I promised I would come with the test done by today, but you know that you took my weekend. So my plans to be in my garden on Saturday, so Sunday I do the market. So I changed plan. Sunday was garden day. The Bible says, when the man was planting corn, they said they complained that it is Sabbath day. Jesus said, if your cow fell in a ditch on Sabbath day, would you leave it to die? Isn't that in the Bible? You got an idea? Do you have such a surah in the Quran? No idea. Okay, so the section for electrostatic cell, we did a test. It should have been nice to conclude it today by kind of revising as we do the solutions. But those questions are all in the notes, isn't it? What is in there? The question on finding the electric potential and surface charge density, and then drawing the sketching, whatever is on is in the notes, is what I did last time. The other ones, you use the Gauss's law, divergence of B equals to rho, but if you want, you can say the divergence of E epsilon naught equals to, then you find the volume charge density. So the issue was to make sure that you look for the divergence of that, where the gradient operator is the Kali by Kali x, I plus Kali by Kali y, j plus Kali by Kali zk. You do the stuff, and that means you get, but also E was equal to minus grad B, so that you get the, I don't know what was given. I don't have the questions here. You are given V, so you look for E. Then for charge density, you look for that. The other one was there part of deriving Poisson and Laplace's equation? I don't have the question here. I didn't want to know anything about that. So we got the second section of the course as we tried to lay a background for the key part, which is Maxwell's equation, that leads to the propagation of waves. So as we propagate waves, we can do it either wirelessly, like you do normally receiving the Wi-Fi, or actually with wires, which is becoming obsolete. You hardly find these telephone lines hooking up. I think we still got a line around out here. We used to have one, but I don't see it these days. Because even now you can use the voice on the internet, protocol phone, voice on the internet phone. So you can have, you can plug into the internet switch and then be able to get because the cabling for internet is already good enough to take your voice phone if you wanted the landline sort of. So we now need to understand the conductors if we want to transfer our electromagnetic waves using the conductors. And conductors, we say that they have a vast number of free charges, meaning that we shall be talking about the current. And the current is the flow of electrons, although the current flows opposite to what we think is what constitutes it. Very funny. When electrons are going this way, we say current is going this way. And we say that electrons carry the current. So the second section of this course, we look at stationary electric fields. Stationary electric fields in conducting media. In electricity and magnetism, we said current, electricity, or steady current. Now we are trying to make it sound nice and towards where we are going. Stationary electric fields, because we're talking of our key thing. At the end of the day, we shall be dealing mostly with the electric field lines and the magnetic field lines. So we want to know how the electric field lines behave in conducting media. And we are using the word media because at the end of the day, we shall be interested in knowing how propagation is done. So we just get a reminder of electric current. A few basics about electric current. And we consider a charge. Consider a charge crossing per second a section of the conductor, section of the conductor of uniform cross-section area, uniform cross-sectional area, A. So if this is the conductor and has got a cross-sectional area A, and then we are having a conventional current moving in this direction. I. The down electrons will be moving in this direction. So this will be the electron flow. Just a reminder that the current, which is the rate of change, the rate at which charges cross a given point at a given time, but we can express it in terms of the, if we took electronic charge to be negative, and then to be the number of electrons per unit volume, times the volume itself, and then times the charge. And then so where n is the number of free electrons per meter per unit volume. And this unit volume is a meter cubed. Vd is the drift velocity. E is the electronic charge on the electron. But I just want to make sure that we agree on this. If the conductor was of length L, and we have as the input, we have, if electrons were to drift from this point and get out here, at this point, if the current is going out here, it is like when you have soldiers moving in the marching on Independence Day, And then the whole section, which is 3 by 6, those are 3 by 6 is no 3 by the section is of I think 12, 3 by 4. So when these soldiers are moving, if there were no markings in the pitch, and then maybe you are just filming them in the middle of the pitch without seeing anything relative to their motion, you may never think that they have moved. They are uniform, they are carrying the same stuff. Normally they are chosen in their kind of height. You may think there was no change. If they move and then they say halt, you may wonder where did they come from? Because almost the whole pitch moves at the same place. So they drift. So if in 1 second, for 1 second, this is not part of the notes, I'm just trying to make sure I explain why it's like that. For 1 second, if they were moving with the drift velocity VB, and they have covered this length, then this drift velocity, the velocity is the same as distance over, which will be L over 1 second. So the VB is equivalent to the length. That's why we get the current being the same as the charge. The charge is the number of electrons in this part here, this section of length here, then multiplied by the charge on each electron, and then multiplied by the volume. Volume is the area times the length. But the length, from the idea that for 1 second, if they have drifted through this length is the same as the drift velocity. So the volume will be the area times the drifting velocity. So this is our charge. The current is equal to the charge over the time we are taking for 1 second. And that's why we are getting this as minus ME A V. So when you had me try to say that this is the number of electrons per unit volume, and then times the charge on each of the electrons gives you this times the volume, then it gives you the total charge within that volume. But current is the same as that charge over that time for drifting, and we are taking drifting for 1 second, meaning that we are having it over and then ending up with this. So I don't want you to do that now, but current is over time. So where is the time? The time is 1. And that 1 second is the reason why we are looking at the drift velocity being equivalent to the length of that volume, that piece of the current. So in exam, whenever you do such kind of thing, you just close through. You don't have to overlap to show that this was what? Rough work. So I go on here that when we are doing this, now that we know the current flowing in the current, we got an area, then we get concerned of another parameter, which is the current density. The current per unit volume, which is the same as the charge per unit time per unit area. So current density, the current density denoted as J is the same as the current over the area. That's the number of electrons that will be going through a given area, and compared to what we have just gotten up there, our current density will be the same as minus NE, and then we divide by A, so we remain with never. Is it never or now it is never? So it will be VD because the A disappears. But this is for when we are concerned of, or when we are able to find out the number of electrons in that volume. If we couldn't count this number of electrons, then we can generalize. And in general, the current through any surface S, the current through any surface. This was a nice looking surface of cross-sectional area A, but it is just any surface, any regular mirroring surface S, then is given by, we integrate. So we get the current being the same as integral over this surface S, and then we get the current density dot ds. Some of you may want to write it as I being the same as integral over the surface S, then you have J dot MDS. So I don't want you to be confused by this nomenclature. By the end of this course, I want you to have freedom in understanding this. So that means for any surface, we can find out the current being equal to that. So I have a lot of garbage here. I'm saved, but I'm able to write nicely because I was able to salvage my ideas. So, for any surface S, we can find the current density, the current being the same as J dot ds. So we're gonna have this. I'm gonna take this volume, this one here. After taking this volume, then I house charge here. It's arbitrary. We have a surface here, which is this surface here, enclosing a volume, which so we have charges inside here, and these charges are slowly escaping through the surface. So whenever these charges escape through the surface, so when these charges come and are moving out of this surface here, they are charges. Now when they go through the surface at a given time, then we get the I over A for when it is going through this surface. And then this one gives us the current density. Now when you have this current density here, the rate at which these charges escape from this surface should be the same as the rate at which the charge is being lost from the volume. Once I have charges inside here, and they are slowly moving out of the volume, of course charges, whenever you have charges, if there are other charges around, they will start getting attracted. So if these charges start escaping this surface from this volume, or volume charge density rho, then they do so by the fact that the rate at which they are escaping equals to the rate at which the volume is losing the charge. And that should be synonymous with what we have covered. If whatever is being lost is equal to what is going out, then that means there is conduit. If the rate at which we are graduating you is equal to the rate at which we are, for example, admitting students, then there is continuity. Our department will be always having students. And this brings us to what we just walked through, almost crammed it. I tried to explain, but some of you were not interested. And we called it the equation of continuity. But for now, we want to look at it in terms of the conservation of electric charge. But we shall conclude by getting the equation of continuity. So electric charge cannot be created. Electric charge cannot be created, nor simply, nor you can't destroy charge. That's why normally I'm so keen, I say no two charges, they continue being together. They know they can't be destroyed. Neither can I create them. They do it intentionally. Famer, what makes you, I want these days to start chopping wires. What makes you sit near each other, these ones, those ones? Do you just want to prove a point or?
The other side is safe.
The other side is what?
It's safe.
What do you mean by safe? They could just make the guy be in the middle. I have no problem. They can still loom over between each other, but these ones for them, they are. You don't want but be between you. But you were near you. You were near you. There's no, these ones I've seen them, but I'm pretending that they are different places. I don't want to have problem. But from next lecture, I will not be nice. Today I just want to finish this section. That's why I'm not rather so much. But from next lecture, I'll be so. So we consider surface, which I've already noted. Consider surface S, which is enclosed in. So you can imagine if I had a Susan, I would be even be told it is time to go out. If I keep singing the same song, when there is no Susan here, if there was a Susan, I would suffer. Okay. Which is enclosed in the volume tau. So we have. The drawing is to depict this arbitrariness of the surface. It is this one has nice sharp points, but assuming it was, I don't know whether I can make it look like this one. So if we have the charges being lost through the surface in all other sides, all corners. These charges, by the mere fact that they are moving, then they will constitute, at a given point time, t, they will constitute a current. And when they constitute a current, if this is having volume charge density rho, and has a volume tau, and then of course this would be our current density. The net free charge escaping through S, the net charge that will be escaping through the surface S. This surface I showed you my paper back. The net free charge, escaping through S, escaping through the surface S during a time interval, delta t, must equal to the net free charge. Must equal to the net free charge. It's equal to the net free charge lost by the volume, lost by the volume tau during the same time interval. During the same time interval. So, the charge flow through S, the charge flow through S Q. What is Q in terms of the volume charge density? Volume charge density is the volume, the charge over volume. So the charge will be equal to the charge density times. So this will be minus integral rho d tau. And what will be the current? The current I will be equal to this charge per unit time. So this will be the same as dq dt, which will be the same as minus d dt of the integral rho d tau. You are mathematicians. I have forgotten my math. From the rates of change, which is the first principles of differentiation, Backhouse 1, page, anyone remembering the page? This would imply that dq dt, which is the current, will be the same as minus integral Caliro by Cality, then the tau. This is the rate. This is the rate at which charge. This is the rate at which charge is flowing through S. Is flowing through the surface S. But current through a closed surface previously, but current through a closed surface, not long ago, we said that is given by I equaling the integral over this closed surface S, then J dot, yes. And that means that since it is the surface and we are having a volume here, we can use TWINAMASIKO Baking theorem. Yeah. Using TWINAMASIKO Baking theorem. I am not TWINAMASIKO, I am TWINAMASIKO. The proud people who say TWINAMASIKO. Those who ask for tips and tickets. So I would be the same as the integral. We take divergence of what was being dotted with the S and then multiplied by the tau, or integrated with the tau. So this would be the same as integral over the volume tau, then divergence of J tau. Please don't put a circle here. You cannot integrate. There is no closed volume. The volume is large, is diverse in a way. It is the surface which you can go around and form an enclosure.
Is
So that's why we put a circle here in the integral here to show that we are integrating over an enclosure, which is a closed surface. So, using my theorem, I wanted to make sure first you see the spelling. So, using my theorem, we will have that this other side here, this now side of I, which was equal to this, now is equal to this. So, the integral divergence of J d tau is the same as the minus integral Kali rho by Kali t d tau. For these two integrals to be the same, the rest is just an instruction of an integral, so the integrands should be the ones which are equal, because the rest is just an instruction that integrate. So it is what we are integrating that we will have these two equations to be equal. So this would imply that the integral, if we can bring the other side, this side to this side, plus Kali rho by Kali t tau would leave nothing on this right hand side. To envision it now in a closer way, if this is the case, the other two, the integral symbol and the with respect to tau are just an instruction. So it is only the integrand which can lead this integral to 0. So this implies that, so for an arbitrary meaning that it is not the one which is 0. So for an arbitrary volume tau, then the divergence of J plus Kali rho by Kali t equals 2, or you can write it in a more elaborative way, that the rate at which the charge density is diverging from this volume is equal to the rate at which the charges are being lost or escaped. I want you to get this point very nicely. And this is the equation of continuity. This equation of continuity says that, this is like a pot, just put like this. So we are having charges escaping. They are escaping through a surface of area. Charges escaping through a surface at an interval. So that if you have charges escaping through a given area at an interval delta t, this one alone gives us the current over, and this whole thing gives us the current density. This current density is diverging, it is going in all directions. That is how we depict it as divergence of. The current density is diverging because of these escaping charges. So that is the divergence of D. This we are saying is equal to the rate at which the charges which are depicted as, or which are derived from the volume charge density, the rate at which they are being lost. The rate of these charges is Kali rho by Kali t, and the word lost is depicted in the the negative. So that's why we are having this equation that as the current density diverges, which is due to the charges which are escaping, this is equal to the rate at which the charge is being lost, from this volume. The negative is depicting the loss. And these two are equal. And if they are equal, then we talk of the canoe. Canoe, let me tell you, me. Charge you. These days, okay, those days when I was, it was worse when I was in, when I had just graduated. These days I've improved in accent. I had a boy who couldn't even hold it. I warned him, but when I reach and I start doing base 2, they say 47 plus 32, then you Kasukwe, 47, 32, poor boy. But I had told them that I have a tongue problem, so they would, others would feel sorry. It's imitating our man with a problem, he's going to have issues. But I used to take it easy. The only thing I'm proud of is that I never got a nickname for the time I taught secondary. I didn't. I would teach these S2s, I'd say momentum, they all sing momentum. When we reach another section, it changes to electrostatics, and they can't, now they figure out, should we call him electrostatics or momentum? So they failed, but here they call him which is not a physics bit. Have you now understood the physical interpretation of this equation? As you diverge off the, okay, not as you diverge, but as charges get lost, they constitute a current, and because they are piercing through the enclosed surface, they now metamorphose into the current density, and then eventually we now look at the current density diverging. That diverging sense is equal to how much the volume, the charges are being lost, which is this Calero by T negative. So don't just cram. Question of continuity is diverging so minus J. No. Let it flow. Let it flow in our bit. So that means that with this in mind, and because we are now dealing with the conduction of our electric fields, to make sure that we send the message across as a medium, then we need to know a few more things about the charge density in a conductor. For an ideal conductor, the charge density inside was 0. But for any conductor, the current density in a linear homogeneous and isotropic medium or conductor obeys Ohm's law. In microscopic form. That is in a physical form, it is under physical conditions of pressure, constant pressure and temperature. The PD across the conductor will be proportional to the current applied, and the proportionality constant will be R, which is the resistance. Now, but here the microscopic form is given by sigma E, where sigma is the electrical conductivity. Is the electrical conductivity. So this would imply that if we took the divergence of both sides, this would be the same as sigma divergence of E. Now, if this is possible, if and only if sigma is not a function of the coordinates. If sigma is a function of coordinates, then it will be affected by this gradient operator. So it is only if and only if the sigma is not a function of the coordinates, whichever coordinates they are, whether spherical, Cartesian, or cylindrical. So, but divergence of E looks familiar. So divergence of E equal to equals to 1 over epsilon divergence of D, because D is equal, and this is if rho is a constant. So hence, our divergence of J would equal, it was supposed to be equal to sigma divergence of E. So now we get it as sigma of epsilon divergence of D. But when you try to diverge the electric displacement vector in a given material, what are you trying to do? Where does, if for example we have two plates of a capacitor and then we have the electric in the middle, when we are drawing of the electric displacement vector, where does it come from to? We got two parts. We have free charges on the plates of the capacitor, and then we have bound charges on the surface of the dielectric on either side of the dielectric. Electric displacement vector runs from where to where in terms of the free charges and the bound charges? Fred, with this, if this is the capacitor, this is the plate, positive plate, this is the dielectric, this is the other negative plate by the fact that it is connected to the positive of the battery. This is the negative of the battery. So, and then here you get a positive bound, and this is the negative free, positive free, and this is the negative bound. Okay, so electric displacement vector runs from where to where? Electric field intensity can run from either, but let me not cheat for here. So if I'm to draw do I draw it from here to here? Do I draw it from here to here? Do I draw it from here to here? Because there is a negative, it is a positive charge here, a negative bound one here. There is a positive charge here, there is a negative free one here. There is a negative, so it will be going this way, this one here. Then there is this one of the induced one, which moves in an opposite direction due to polarization. Remember when we had P over epsilon? So D runs from where to where? With my A, B, C. Which one is D? Yes, friend.
I think it is B because B is the divergence of the free charge, the free charge base.
Where are you getting the divergence? We are only looking for D, then we talk of, I haven't even written, I'm supposed to be saying, but divergence of D equals to something.
Say my answer is wrong.
It's okay, Carol. Where it runs from where to where? Which one is it? A, B, C. I am asking Carol, why are you impatient? You don't trust him or what? Carol, which of these is our, which one of these represents the electric displacement vector? Where is it? Did you put up your hand thinking I wouldn't see you or something? I have a problem. Even if I'm looking this way, I can tell you what you guys are doing. When I'm busy concentrating, like that one raised the hand like this. Okay, Kasada, it's B. D. So it runs from free charges, positive charges to free negative charges, meaning that as you diverge electric displacement vector, it's all about the free volume charge density. This is why I wanted you to know how rho free comes about. We did say that divergence of D equal to rho and sigma equals to because when we talk of sigma, we are talking of surface charge density. So you're talking of the electric displacement vector, but normal to this surface. So this would be this the sigma. When you are deriving the energy density, you needed to say, but rho, sigma equal to this, and rho would be equal to how much the charge density would be how much you are able to stretch through the electric displacement vector is able to go and diverge through the material. I don't want, in this course, I don't want you to plan anything. I want you to understand it. Okay, so we'll move on with algebraic gymnastics, where rho free here is the free volume but from the equation of continuity, which had this, which told us that the more, the way the current density diverges is related to how much charge is being lost. From the equation of continuity, which states that the divergence of J equals to minus Kali rho free by Kali T. This would imply that divergence of J is the same as sigma over epsilon divergence of D, which is rho free, and this is the same as minus Kali rho free by Kali T. And you eat your sweets without making that sound. See those kids, those well-to-do kids in school who would come with nice sweets, they would make sure they touch those papers to show you that they got sweets. So one of those. So, once we got this, then we can say that hence if we can integrate both sides and rearrange properly, we can put rho free this side for having, since we have the change of free volume charge density, and since we have sigma there, we can take the time the other side. So we have sigma of epsilon integral dt equals to the minus integral carry rho free, then we divide by over rho free. And from my little mathematics, when I integrate what is being differentiated, I do no work. So then I remain with sigma of epsilon being the same as I integrate 1 over rho. So this would be natural log of rho free, and normally we would be having something to do with constant of integration. So this would imply that this is pardon?
When we having on this side of the free charges, how come we are having a partial derivative and yet for the time we have changed it to a full derivative?
Well, I'm sorry.
It is me who told you.
You can now do this spread. Now
Even here we get it.
can
When
make-
we integrate the thing, we
you
get it.
can make it a full derivative now. I'm sorry about that.
Even here,
When
when we integrate the t, we get t.
we get it here. Yes. What did you eat in the weekend?
Connected to reaction.
So this would imply that rho free t, okay, as a function of time, would be the same as exponential, because this is log to base e of rho free, so it would be exponential minus sigma of epsilon t. Constant when at time t is equal to 0, there wouldn't be any free charge density, so the constant is not every day do we have to put a constant. If we can't, that constant will end up 0 if we apply the boundary. And thus, we got rho free valuing as rho free at time equal to 0, exponential minus t over tau, where, do you remember tau? Yes? We would not, what?
Negative, that's similar.
With what? This one here. Okay. Does that solve problems? There's a negative here. Sometimes when I'm writing, I'm rushing, I want to finish this steady current today.
Yeah.
So, so where tau, which would be the same as we just said tau, this is a t here, and we are dividing by tau, so tau would be epsilon over sigma. Yes?
When we integrate that whatever that function, I would think that when we say we are going to integrate from rho free at t, then rho free at, when we say rho free at 0, then rho free at t. So that we have that expression there.
So that we have this one here.
Yes.
Okay, if you say so. This is the same as relaxation time. You guys are really, but I like that. I like that now you are not taking things just for the sake. Whichever, as you can't say integrating from 0 to t is they are not definite still having T being ambiguous or ambiguous. So if it was a definite like 0 to some value, or T1 to T2, then we would understand what T1 and T2 would be. But we can't say it should be. But this one is just to show you that this would be the same as the raw free at when we start at 0. And the rest, we still have the T. Do I make sense?
Yeah. Yes.
Okay. Check.
I don't love grief.
Is this the spelling? So you go to Greece, I don't remember the page, and then you find out how it is derived. The issue is to know how the charge density varies, this free volume charge density varies with time, with conductivity, and of course the permittivity of a given medium is constant. Now, the relaxation time is the time between two consecutive collisions of either electron to electron, electron to atom, or electron to a lattice. Lattice could be a bunch of other electrons, atoms making up a given structure. They have to be lattice. You don't know a lattice? In your solid state physics. So yes, you had the
Estimates is the relaxation time. I thought tau is volume. So
that's why we are defining it, where tau, that is equal to that. In physics, you are allowed to say where Isaac is an animal. As long as you have defined Isaac. You get the point.
we are looking at tau as time, not volume.
At this point, it was so necessary that we say where tau is relaxation time, because now we're talking about conductivity. Not long ago, when we had our volume and the charge was escaping from it, tau was volume. And I remember telling you that you have to be flexible. You will see rho being the volume charge density, and the next step, the next section, it is now the resistivity. And as you can see, that's how we are now. All along, previously, we have been seeing tau, volume. Even now, a little bit. But now, when we reach steady currents, tau is being relaxation time. From whose model? From Drude's model. Drude said that electrons are the key essential part within an electron, and they do so like they follow Brownian motion. And then we were able to look at before you apply the potential, they are moving in a random motion as long as you are above the room temperature, and they do so in a random way, like that smoke in a glass tube, a glass container. Once you apply the potential, then they get accelerated. When they get accelerated, other issues come in. So you get the drift velocity, and then you get also the electric force, the damping force, and the driving force, which is emanating from the applied PD. And then the rest is algebraic gymnastics. Eventually, we are able to find this, and then from this, that's where we got the J equal to sigma E once you get the concern of this being the potential gradient. That is the electric field energy. So this, the relaxation time, imagine between two electrons knocking each other. And if you go to solid state physics, maybe even the properties of matter. You can imagine the size of an atom. And then you can imagine the distance between just a couple of electrons which are orbiting a given shell of an atom. And so you think the time is in which amounts? For an electron to get a chance to knock another electron, or to knock an atom, or a lattice, if it is just being lousy. So the relaxation times in characters, the reason I'm trying to ask that is that some of you will get relaxation time being like 20 seconds, and then you write it there. That it will take an atom to knock each other by after 20 seconds, 20 times the one breathing in. 20 times, and then you think an electron will take all that time to knock another electron. In a structure like my body, or in a piece of wire, and you write it and underline, and walk out of a test with the head high. Just because you got an answer and then you are comfortable, you should question yourself and say, but is this real? Some things have to. So relaxation times in characters are extremely short. And being short, e.g. for copper, it's approximately about 10 to the power negative 14 seconds. So you can imagine the time and electron. That's why when you touch a wire like this, then you are shocked, because the electrons are moving at a high speed. But I still wonder how these people are able to figure out. I know Voltaire was just doing his work on dissecting a frog, and then it was already dead because he had already killed it. And when the tweezer touched, I think a scissor and the tweezer touched different parts of the leg, and the leg kicked like this. So it was like, how can it kick? I've already killed the frog, but the frog is busy kicking. So he tried again, it kicked again. So he realized that there is some electricity. And then because there were two different metals, and then there is some solution, like fruits of the leg of the frog, that's where the barrier came in. But you have the positive plate, the negative plate, I think lead and copper, for example, and then you have sulfuric acid in the middle, and then you have charges moving, and then you constitute electricity. That's how a car battery works. You see the humble beginnings. You can't get those humble beginnings to understand something when you are lousy eating potatoes. These people in Masaka who grow coffee, the local person who doesn't even know the word coffee in English, they will tell you everything. When you see those flowers coming up, do this so that they don't fall off. Then probably have bees around the corner so that they help in nano cross-pollination, so that you don't have contamination. Something like that. But these ones who go in suits, they have red, they say pollination is, you know, this. That's where the problem is. But the other old man cannot transfer his knowledge. When he dies, that's why they say when the owner of the home dies, it is climbed by frogs, because all his home knowledge goes with him. It goes with him. The boys now start looking for how to sell off the things. And very few of you talk to your parents to ask how things are done. When you reach, you are just telling them at campus. You are not free to talk to your parents, you want to detooth them. So you are doing a lot of photocopying they want to photocopy this, or you want to look at Njawolo. Instead of sitting with them and you get some wisdom. Your unhonestness, you can't talk much, you want to be truth and go away. They are not tough. You have to learn to talk to them sense, not going to steal from them. How do you feel when you steal from your bed?
Why is the family?
The men is in the family when you come here and they also tooth you and take it away. You reach here, they steal it from you. Someone say, take me out, takes everything.
Why is it? What if we have not stole from the
Which vice versa? The ones who steal from you don't have time to steal from their parents. They know they will get from you. We need to enter a character and understand what is going on. And this is the basis of microscopic form of Ohm's law. We consider a homogeneous character, uniform character. We consider a homogeneous character of uniform. Being homogeneous doesn't mean that it has uniform volume. It can mean cross-section area. It can be uniform in structure, but when it doesn't have uniform cross-sectional. So when I say homogeneous and I say uniform, and then I say uniform of uniform cross-section area, you don't say I have repeated myself. The other uniformity is in structure, in nature. This one is in a physical form. So consider homogeneous character of uniform cross-sectional area. Cross-sectional area. In which a steady current I is flowing, and then that means that we are having the character of uniform cross-sectional area A, and we are having a current I flowing flowing through this character after applying the PD V volts. If it is of length L, then the current I we said would be the same as the integral J ds, and J is sigma E, so this is this would be E ds. Now, if a PDV is Benon, if this PDV is Benon above the ends, or at the ends of this character, above the ends of the, above meaning that you are just putting here and here, so it's not about being just above. It's on the character. Above the character, above the end of the character, by an external source, like battery, Then we, from E is equal to minus grad V. Then V grad here is length L. That's the kernel we have. So the potential would be the same as integral from 0 to L E dot dl. And this should, where L and Y use, we have been using small l.
Yes.
So since we have this small l for the, so we take, let's take, since this is l for the variable, let's take this one, the length being capital L, for purposes of having a difference between what we are integrating with respect to. So, where L is the length of the conductor, where L is the length of the conductor. It should have been a minus somewhere, but that would be when you are moving from the high to, if we were to say from L to 0, then we would have minus E dot. So the resistance, now, when we are using a conductor, we also have to be considerate about how we resist what we are using to transfer the electric field. When we are transporting the current, we can transport the current to make sure that we have that as a component of our field. So then we need to know how much it is being resisted. Yes. Yes.
I think we have a electric field dotted with where is supposed to be.
Yes, the vector symbol should be here. So the resistance is important in order for us to, because once resistance comes in, then we have loss. We get power losses. P equal to I squared. That's why when we are getting electricity from Karuma, bring it here to Kampala, then you have to make sure that you take interest in this one here. So that's why we step up. So when you step up the voltage, so if Vs over Vp, how you step it up is inversely proportional to how it affects inversely the current. So you step up the voltage at Karuma, the current significantly gets stepped down. The losses in heat losses, they get significantly down. And then when you reach here, when you reach Kawanda, you have again to make sure it is usable. So you step it down, you are going slow, short distances, and because you are going short distances, so now you don't care about the resistance, because it is now for short distances. And that's why even these cables of electricity, as we are going to see soon, they have to be huge. So A has to be huge. Otherwise, we would be economizing and using one strand of electric wires. But you see, electric cables are huge. You see a whole big thing, like you have 5 still small wires inside, and then aluminum, like another 7 or so also wound together. The ones which people steal for using as hangers. Do you know how to make hangers? What do you do in your life that is interesting? So where L, I think I started doing all that. Where L is the length of the current. Then we can now talk about the resistance. So resistance, the resistance Please don't tell me that R should be small. Of the character, the resistance of the character is defined as the ratio R equaling to potential over the current. The potential, we just said that is the integral 0 to L E dot dl. The current, we just got it as sigma integral, which was previously J dot ds, ended up substituting for J to be this. One on top is in a line, the one down is in a surface. So that is not an issue. The issue is that once we get, we can use the integral to find the total surface area, and then we get the length. So if we have a uniform or homogeneous character, for homogeneous character, as we began with, of uniform cross-sectional area, A, and length L, then we have the resistance being the same as E. E is, we have our character, then we have I, we have L. So this E dot dl is the E magnitude, the L magnitude, times the cosine of the angle between the two. So dl, what would be the angle between the electric field intensity due to this conductor and the dl? I want to see whether you get an idea of how this comes up. Isaac, since you are busy telling others to tell me. I'm asking the question so you are transferring it or what? What is the angle between the electric field intensity? Okay, where is the direction of the electric field intensity when you got a current like this, current line? Yes. Perpendicular to the? Okay, so he's saying that this is E. Is it true or not? For sure, what I'm sure about is that this being our ds, okay, the total area is A, but for a particular part here of area ds, elemental area ds, I mean ds without this, normal to this gives us the ds. Okay? So there we have at least where the ds in this other part acts, which is most likely the same direction it does with this. True or false?
True.
So when we take that product, we are having the magnitudes, then the cosine of the angle between. So where is the electric? The question now is, where is the electric field intensity active? Which surface?
Surface area. Like the angle between the
You are just working backwards. You just want to make sure the angle is 0. So, but we wanna get the actual, where would be the electric field intensity be active? We are having the current flowing. When the current is flowing, yes, before I.
Since the current is flowing in this direction, and the electrons are had to be flowing in the other direction, right? The field is flowing in the direction.
In other words, we get the current flowing from the positive terminal to the negative terminal. So we can easily find out that the electric field intensity is moving in this direction. So this is what we can only, this one we did it when we were having the line of charge, remember? Yes. And then we drew a Gaussian surface around the, so we already had a charge on the line. Then that means we were now having the field coming out of the line of charge. But this time we got a conductor having a current flowing in it. And just the mere fact that we know where the current is moving from to gives us the type of charges where it is coming from and where it is. And then so that means we get, so I just didn't want you to cram this too. That it is this integral over this, then now we just say it is equal to E, then L over, then sigma E, then the area, the whole, this was the main, so the total cross-section area would be the A we had on the diagram, which is the cross-section area. So the reason is that we get the first bit here being the same as E dot integral 0 to L, E dl cos 0 degrees over the sigma integral E ds, then cos 0 degrees. The E's go, okay, become magnitude. This one is 1, 1, so even if I'm cancelling it, and then here we have the, we shall end up with the L after it, so integral dl 0 to L, which is L, and these ones go, which would be the same as L over sigma. But we know that 1 over sigma is the same as rho. So this is rho L over, therefore, the resistance R, I just want to put it this way so that I can say a couple of things about it. So therefore, resistance can be given as rho L over A, where what we are having as rho is no longer volume charge density. 1 over conductivity is the same as the resistivity. It's called resistivity. It's the inverse of conductivity. So this is the reason why we make sure that because resistance would be big if the length is long. So that's why I told you that from one cross on the pole of electric pole, you have the insulators there, and then normally what happens, a short distance of these cables goes, and then this one is also connected, but they are not connected together. You get a bit that you just wind here, another one here, wind here, another one here, same thing. So you have short distances of these kind of cabling. Two, so that is the L bit. Two, you will find that cables of electric cables, they are, I don't know how they call it. You find that there are many aluminum on top, and inside there is another bit of the steel. To make sure that A is very large. So a large A makes this equation small, and when it makes it small, you get a very small resistance, and then you lose. If you have also tried to step up the voltage in this rate here, the current goes down. So that's why we hustle. Yes, the power is in Karuma, but you after producing it, you don't just find, you might imagine it is in Karuma, but you find the people in Nidira still using a Greek or something like that, because they are still trying to make sure it is transported. Or you find the cables are just passing over your house, and you have no power, because it is high, it was stepped up for easy transmission. To get it in the house, you have to step it down. And there are many communities around, because they are built together and increased over time, you find that their power is always dodgy like this. Because their transformer is not able to step down what reached there, a value that would be appreciable for the community. It is overloaded, so it keeps whatever. So here is a take home. During the transmission of electricity, we take care of the resistance by making sure that you use big cables. Otherwise, we would use just one wire from Jinja or from Karuma to here. You save. But then the smaller it is, the more the resistance. The more the resistance, before you know, it is already warming up. It has heated up. You see it already hot. It snaps. And then, so this is how we avoid the losses of electricity. So, and that's why we studied transformers in, I don't know whether the electricity and magnetism, but in all level. We teach transformers so that kids know why do we step up the electricity, reduce the loss. When you reach the radio, you also need to change the 220 to about 12 volts for your radio. And then use the bridge to rectify it. Because in electronics we say most of the circuits use the DC. And then after using it, then when you go to an oscilloscope, again it is stepped up in order to get enough of it to eject the electrons at the CRT, at the cathode. So when you open up a TV, a Nyash TV or the oscilloscope, you'll find there is a section where there is a step-up transformer that gives high voltage, HT, to the cathode to release the electrons that would be used to give you the waveform. The Nyash TV, the ones with the pro-rolling in the arm. Pardon? So, but that is about just a connector. We don't use this just bare connectors just moving around. Most times we face with when we have one inside the other, which we call coaxial cables, like the ones of the antennas of the TV. So next we look at the resistance of a coaxial cable. Axial shares an axis, concentric shares a center, co-wave shares. So resistance of a coaxial cable. There's no break, so there's no break today. I want to finish this. Two perfectly conducting coaxial, two perfectly conducting coaxial cables in form of cylinders of length L, inner radius A, inner radius A, small, another radius B, small b, and named the potential, named a potential V, and enclose a material with the army conductivity sigma. So it's dirty, but this is what I'm talking about. Share. Also that chalk, that can be also like that. So those banana cables, though at that point, those are the two cylinders that I'm talking about. So the one cylinder is inside, which is the way you touch like and the inside one is the cylinder, and the separation between them is what we are saying is an ohmic material of conductivity sigma. So that part of the banana cables that are going around is the two cylinders. You have the outer cylinder, and then you, my friend, I told them that some of them are doing what they are wanting what they are doing, not doing what they want. So this is the outer radius B, this is the inner radius A, and the material, that material between them, which you see, those are two, one is male, the other one is female. If you want, you can see how the male goes in the female. So these are named at the, so you have positive here, and then you have negative on this other one, because they are named at a potential V. So now we can say that E, the electric field intensity, since you have this one being positive, inside one is positive, the outer one is negative, so the E is radial. So we have E being radial and perpendicular, of course, to the circumference of the cylinder. So E is perpendicular. E is perpendicular to the electrodes. card cable. So that with no free charges, Gauss's law in differential form, Gauss's law in differential form says that, or which states that the divergence of D, which is epsilon E, is equal to 0. It should have equal to rho free. But if you are not having any free charges that are crossing from this, because you are not having free charges crossing from this side to the side. So for cylindrical symmetry, the reason we did the Laplacian stuff, so for cylindrical symmetry, then we can say that 1 over this divergence of this is the same as 1 over R Kali by Kali R Kali V by Kali R equaling 2. And if we integrate once, everything becomes a constant. Integrate twice, then we get integrating this symmetry expression, then we will have R dV. If we took for the other part, the R will be equal to A, which is a constant. Integrating again on rearrangement, which implies that dr was equal to A over R. Integrating again, not doing anything reasonable apart from doing the light gymnastics, so you shouldn't accuse me of anything. On integrating again, we are integrating 1 over R, so this would be the same as VR, being the same as A natural log of R plus some other constant, where B is another constant. And this constant here is found by looking at the boundary conditions. We are considering the coaxial cables, so we use cylindrical coordinates. And if we are using cylindrical coordinates, we are not having any variation in the azimuth, like nothing is changing. The cylinders are uniform across. The material that is between them is also, so at the azimuth, everything is constant. And then the length is a particular length that we're going to take, or we can take a particular length, or we take per unit length. So there is also no change. Once we connect to the outer, we ground the outer one. It is negative in the diagram, but that's more or less like if we grounded it. Okay? And then we'll give, remember the V naught we gave the inside cylinder. Once we do that, it is uniform across the Z. So there is no change in Z, there is no change in terms of the azimuth. What is remaining is how the variation is taking place as we move through the material in between these two cylinders. And that's why, for example, when you look at the cabling of the TV antenna, then you find that the mirror coming out wire, but this is very thick. But then after this, you have some aluminum foil before you have a mesh kind of on top. The reason for this foil here is to avoid what they call crosstalk. Crosstalk is when you have feed lines moving from here in the middle to the outside. So then you get interference between these two. So the aluminum foil reflects them, but you can't have them going through comfortably. So then you get your nice signal. Otherwise, we would have just like two wires, like how these banana cables are, and then you get your signal and put it in the house. But you see how huge the cabling of the TV antenna has to be because of taking care of these issues of the two parts of our signal. So integrating again, we got that, and if the potential at B is equal to 0, this is due to grounding, which I labeled as negative, but it is actually grounding. On that banana cable, you see that whether female or male, that other outer part is metallic. Doesn't matter. It's not insulated, it is grounded. You can hold it if you want. So then if VA was some potential V naught, so this would imply that 0 is equal to A natural log of B plus the constant B, implying that this constant B is equal to minus A natural log of B. Therefore, VR would be the same as A natural log of R plus some constant which we are seeing as minus A natural log of B, or we can write it as VR being the same as A natural log of, this is R over B, this is the minus. Now for the other condition of VA being V naught, if the potential applied at the inner cylinder is V naught, this would imply that V naught equals to L in B over A over B. And this would imply that A would equal to V naught over in A over B. Thus, now that we have the A also, then VR, the potential at any radius R, will be the same as V naught over natural log A over B, and then the natural log R over B. We got a potential. If we got a potential, we can use the notorious E equal to minus grad V to find the electric field intensity. The moment we got electric field intensity, we can use it in form of, since we know that for any enclosed, distribution that has some semblances of charge, then we will be able to find there by using the Gauss's law in directrix, which will be the same as the E dot D dot S being the same as the enclosed charge. And then we would have that, now that we got the potential, we can find the electric field intensity. The electric field intensity. And this electric field intensity, E can be formed from the ER being the same as minus grad V, which is minus Kali V by Kali R. Since the varying current here is in the gradient operator
We are only in the position the
Yes.
simple value.
So why am I still doing the curry?
I mean, why is it don't demonstrate that
Okay, let's
instead
take
of breaking
good. So let's take it as dividia, but. So then we have here being the same as you will not tell me I want to finish this stuff with A over B times 1 over R, and then this will E R will be the same as B naught over R in B over A. And the current density would be given by JR equaling to sigma ER. So JR would equal to sigma over R in B over A, V naught. If I got the current density, I can get the current from I is equal to J dot ds. So then I would be that the current I is equal to integral over the surface Sj dot ds. And this would imply that I is equal to the integral of from, so we got 2. ds in the cylindrical coordinates is the same as R phi dz. What is any one of you with identities, or you just kept them home? So this is from z equal to 0 up to L, the length of these characters, 5 from 0 up to 2 pi, and then we have of course, the current density now, because it is getting out like going in all directions, so we have it changing at each point. So then we have JR, R at the phi Z. Then we would have this as being the same as, I think there should be a JR somewhere. There's a JR. There should be, I feel like, who has the identities here? It should be R dr, then divide Z. Are you sure? I'm sure. Yes. Yes. Yes, we are in cylindrical coordinates. Huh? It's fine. It's fine. It's this. It is. Some people call it phi, but it is phi. It's not that guy. So it should be R JR dr, R dr divided Z. And then we have pardon?
And I think you've done it.
Wait, I'm still moving. So with the other integral is from where to where? You want the one over, right? Because I have these are only for Z and by the one over that moves from where to where? When we are having the DS, when we are looking at that one, for 20. expression for ds from there,
Yes.
for given for particular identities. So that's why I was asking, what is ds, the surface for the
For the S, phi is not a parameter.
phi is not what?
It's not something.
Yes.
You can't see when you are looking at the surface, when you are looking at, this is the cylinder. This is the cylinder, and you want to, this is the surface area of the cylinder, and you don't see surface.
I mean phi, the angle.
Yeah, the angle is here, is around this point. Yes?
But I think the other if you move from the center to this cable to the main, which is R. So you show the integral will move from 0 to R. That's what I think.
From 0 to R.
Yes, from the center of the cable up to certain
Somewhere.
Yes.
But we have a definite, we have a definite structure, which is having two cylinders, one inside, one with A, the other one outside with B. So yes,
I was meaning that the angle is constant if it is a cable. The angle is constant if it is 2 phi.
as you move,
We are increasing the rate and the
Benjamin, as you remember that, have you seen that thing on where that plane that shows you how phi is changing? Here, as you try to investigate what is going on here, you can do it from 0 to 2 pi. As you investigate at this point, this surface here, to see what is happening there. To understand how the current density is being affected, because you're having charges moving out all through. If this was now, after charging it, after putting the grounding here and putting the V node inside. But remember, we are moving from the inside sphere, so the cylinder, to the outside. So I will want you to go on and show that this is why I enjoy being in front of you. Show that R equals to natural log of E over A over 2 pi sigma A. And that seals our section for steady currents. Tomorrow, we shall understand how the magnetic fields interact with the materials under the section we call magnero. Magnets, so magnetic fields, so the static magnetic fields, which is a section of magnerostatics. See you tomorrow.